Okay, welcome back, everybody. So, all right. So today on the menu, I've been trying to change my workflow a little bit for these presentations, and it doesn't seem to be working all that good. But okay, let's try to get through this. So yeah, that should be our penultimate lecture today, and as you can see here, that will be on slug tests. You can find this in your book in Feather, chapter 5.6. This material is in there. So yeah, this is our penultimate lecture probably, so one more on Friday. And so what are slug tests? Basically, they're another way or a new way to do aquifer tests. So we've seen different methods. So when you have steady state reached, or when you have those time-changing, basically pumping tests, right? In confined, leaky, and unconfined aquifers, different methods. Typically those curve matching method, graphical methods, and then a few other ways to get to our aquifer properties, right? So slug tests are another way to do this, and typically this is what they look like. So this is actually a slug right here. I don't know if it's very visible on the screen, but this is a slug that is being dropped into a well, and you can see here this is just a small, simple PVC well, probably some 3-inch pipe, piezometer driven into the ground, right? So very simple well, simple slug. So a slug is actually what we drop into that well. The idea here is to displace some water, right? So if we drop this real quick, now the water level is going to rise, and if we can measure the drop of that water level, now we have a new method to find head as a function of time. As you can see here on this little graph here, we have head as a function of time. So this is just like we've seen for unsteady flow before in the previous lectures. And then from this data now, finally get to our aquifer properties. So ideally, transmissivity is what we get. Storativity is what we'd like sometimes for confined aquifers. And yeah, so this is the general idea. Today we'll do a little bit more introduction, and then we'll study 3 different methods. So this is a little bit heavy, I guess, as far as the number of methods we'll see, but I just want to quickly go through them because they each provide different benefits, and you can see here they go by the name of the original authors that came up with them. So I talk about the Cooper method and the Vorslev method, I think we say, and then the Boer method. Okay. So from last lecture, you will remember that when we have an unconfined aquifer, right? So this is the curve for an unconfined aquifer. We have 3 different parameters to take into account, right? So we have a Wells function, a W function, that is a function of UA, UB, and sigma, right? So 3 different arguments for that function. Now what we'll do today, what we'll see today, especially in that last method for the unconfined aquifer, you'll see that it's similarly complex. It's different, but there's a bunch of different numbers and strange numbers. So I'll try to go through them systematically. Okay, so last time I also reviewed these, when I introduced the slugs at the end of last lecture, I talked about some of their benefits, right? So why do we need them? Well, one of the main reasons is that pumping tests are expensive, right? If you remember that picture from the title slide, you can see that this would be very inexpensive. A slug test, you just have a slug, you can be just a one person if you have a simple piezometer, so you don't need to dewater your well, so there's plenty of advantages to do them, mostly that they're kind of cheap and quick. Again, the idea is to add or remove a known amount of water. When we say slug test, typically we mean we drop a slug into the well and we raise the water table, watch it go down. Now the counterpart of that is the bail down test, which is basically the same thing, except now we pump some water out, right? So we drop the level of the water, and then we look at it go back up. Okay, so that's a bail down test. There's two types of responses that I mentioned last time, overdamped and underdamped. As you can see here, I already crossed that out, so I will not go into the underdamped responses that are a little tricky to analyze because of that, oscillating curve. So now you have to bring in, the oscillating part, and yeah. So I just skip that. This is in your book. If you ever need more information about it, maybe I'll do a separate lecture that you won't have to worry about. But for today, we'll only see cases where the water is well behaved, quote unquote, meaning that it drops, exponentially, basically. Drawback of using slug tests, typically you only get local T and K values, so things that are near the well, and I'll explain that a little more later, but the value you have are basically local to your piezometer or to your well, and they don't really represent the entire aquifer or as far as you would like it to be often. So yeah, there's plenty of issues of skin effects and geometries that I'll talk about later. The storativity is also something that is usually not accessible with those tests. So remember the storativity we get from the dynamic part, right? The S, if you remember the dH dt in those general equations, linearized Boussinet stuff from our chapter 4, right? You get that S from that unsteady side of the equation, but when we do the slug test, usually we don't have access to the storativity, so that's definitely a drawback for confined aquifers. Okay, so this is a general geometry, and you can see already that this might be a problem when you have the radius here of the casing, right? The casing is that pipe that goes into the ground, and the screen itself might have different diameters, right? Now sometimes around, you can see here on the right hand side, you can have a screen inside and then some gravel pack around it that has obviously a very different hydraulic conductivity than the actual aquifer. So if you see here, just to contrast, right, the clay versus the gravel pack, obviously when you do a slug test, you will account for some, again, that's the local part of the slug test, right? Some of that gravel pack with high hydraulic conductivity is going to skew your results, right, towards higher conductivity than the actual aquifer in clay. So we'll see later that sometimes you can identify those things, but sometimes not so easy. And again, the idea is when you drop that slug into your well here, let's say you occupy some volume of water, right? Whoops, this is not a very good straight line here. Right, now you've moved the equivalent amount of water here up top. Right, so now your water table has risen, and you will watch it drop. So you will watch it drop back to the original water level. You would remember that falling head permeameter that we've studied during the Darcy lectures, right? And if you remember, after a bit of math, basically mass balance, we get the hydraulic conductivity, right, is a function of the area of the tube you're using to let the water drop, and then the area of the column if it's different. So you can see here the similarity with those well casings and those like packed gravel that I've talked about before, right? So if those two areas are different, if this is your gravel pack here and then this is your tube, now you have two different areas that are represented here by little a and big A in the falling head permeameter. You can see that L is, if you remember, L was the length of the sample, so that would be the length of your sand or whatever material you're testing. The length of the column, the time is down here, and then some log of the h0 over h1, right? So the original level and then the drop at some time later. So again, this equation here, or this principle of the falling head permeameter, is basically the same idea as the slug test, right? The slug test is the same. We raise the water level and we watch it drop. So what we've studied for falling head permeameters pretty much applies to slug tests. All right, so let's review somewhat quickly again. I'm going through the concepts of the derivations rather than being strict on each and every step. But the idea again is to consider your Q in. Consider your water in equals water out plus the change of volume over time inside the well, right? So again, this is just a statement of mass balance. If you have water coming in, water coming out, and then the change of the volume inside the casing, basically, that would be your total mass balance, right? So Q in, Q out, and then some source or loss term. In the case of the slug test, right, there's no water going in the well, so Q in is 0, and there's water disappearing from the well, right? Again, the water is dropping in that well, so it's going somewhere. So there's water leaving the well, and that is, compensated, or this is the image of the change of volume in the well, right? So as the volume in the well drops, or the water drops, there's some volume that is changing over time inside this well, and that that water that is lost inside the well must be coming out of the well somewhere, right? Okay, so the change. The volume of water inside the well is easy to calculate. This is just pi r squared. So r here would be the well radius, or the casing radius, right? So RC we can call it for the casing. H is the water level in that casing, and then delta T. So now you can see here those delta, that difference equation we can just write as a differential, right? dH dt, and then we have pi r squared dH dt for the change of volume here. Now the Q out here, this term, what is that? Well, you can think of it as, we can go back to almost the beginning of those lectures and invoke that Thiem equation. Okay, so this Q out, right, the volume of water coming out of the well can be related to our Thiem equation from the early lectures, which is basically the steady state equation, right? So we have Q here, and this is our Q out that we're talking about. The Thiem equation, we wrote it in that chapter as the transmissivity equals Q over 2 pi, the head at two different observation wells, natural log of the ratio of the distance, right, R2 and R1, where those two wells are placed. Now again, conceptually here we're in a similar situation, right? So if we think of R2 as the radius of influence, so we can call this RE, right? How far from the well do we have a measurable effect, right, of the slug test in this case, right, or the pumping before, but now of the slug test. So at R2, right, we're saying the drawdown is basically 0, right? So H2 here is basically the same as the original steady state, stable water table, stable piezometric surface. And H1 here, if we consider H1 the radius in the well, so let's call this RW, right? RW. So if we count this, first distance as just the radius of the well, now we have the effective radius, or the radius of influence, if you will. The radius of the well, which can be different from the casing, and I'll explain that again. We've seen in the previous slide, right, the casing can be, say, a 6-inch well, but then if you have some gravel packed, now the actual well, the diameter, the effective diameter of the well is more, because you have that very loose material around. Or if the screen itself is, larger, this should be really the screen radius, not the casing radius, because this is where the water is flowing in, right, or out in this case. And that's where, you know, that boundary is. The boundary is not the casing. The boundary of the well is actually where the water comes in and out of the well. So it can be outside the screen, or it can be outside that gravel pack, you know, whatever that skin is. So inside the well here at R1, right, H1 now is the drawdown, if you will, or if it's actually the water level in the well, right? So now we have the water level in the well, and we have that ratio of, you know, effective diameter of the, you know, of the cone from the well, right? Okay, so now we have everything we need, basically. Now we can just replace Q, right, with its value, which is basically that transmissivity. So that's where we get our hydraulic conductivity here, and then here we're going to have basically 2 pi h, right, and then we have some ratio of some dimensions, right, of the well, and then its radius of influence. So h is what we'll measure, but if we plug that back into our equation, our original equation here, we can see that we have h here. So again, h2 is 0 now, right? So if we call this just h, and not h1, just h in the well, basically, remember that this here is also h in the well, right? So now we have something that has dh dt here on this side, and it has h here on this side. So we end up with an equation very similar to what we had before. That's basically the same demonstration we did for the falling head permeameter, or also for our steady states. All those concepts are the same. So now if you replace everything in, you know, you end up with an equation with 1 over h dh equals some kind of, so let me write this. Okay, so if we separate all those variables, if we plug in the Thieme equation in Q out, and then our change of volume over time is that h over dt dh over dt, separate the variable, you end up with an equation that looks like this here at the bottom, which is 1 over h dh equals transmissivity times blah. Again, blah is a whole bunch of, you know, numbers. Basically, there's some pi's and some r's in there, but we'll see them in a minute. It doesn't matter, but we get this equation, and we can integrate both sides, right? So again, you get, if we integrate this and this, we end up with, you know, natural log of h at 2 points, and we have time. So now, if we measure h as a function of time, right, and we plug that on a semi-log scale, we should get some straight line, right, because we're going to have natural log of the h as a function of time. So again, if we plot h and time, we should recover the slope, which is going to be given by this entire, you know, constants here. So eventually we can extract transmissivity once we know what all the other numbers, so all those length scales and ratios are, we can extract the transmissivity. Okay. All right, so this was all the introduction and sort of the reminder between the falling head permeameter and the analogy with basically a falling head slug test, right? Now, different methods. So the first one we see is the Cooper method, and again, this is sort of reminiscent of these graphical methods that we've seen before. And you can see here that there is basically an x and a y, and then a family of curves again. So there's going to be like 3 different things to track. On the y is the ratio of heads, right? So 1 is at the very beginning, right? We start at 1, and then it's like, you know, drop by 10%, 20%, 70% after some time, right? So here on the x-axis is basically time, and then that family of curve here, you can see now those ratios of radiuses or radies, I guess. And again, RS here is the screen radius, and RC is the casing radius, right? So ratios of R squares, and here you can see the advantages, you get storativity out of this, right? So you do this in a confined aquifer, you get some data, you plot it in, again here you can notice that the x-axis is in log and the y-axis is in linear scale. So you plot your data that way, and then you should be able to line that up on one of those curves, right? And as you've seen already, you know, oftentimes it's not easy to pick which curve it is that it corresponds to. So that's kind of the limit of those graphical methods. But still, you get some data. So let me get my pointer back here. I don't want to draw here. Right, so this is your data. Again, this is, you can see here, log scale on the time and linear scale on the heads. And now you want to drop this onto here, right? So you're trying to match this. Remember your axis, you've done that as problems before, right? Your axis need to match. So you can see here my y-axis is completely wrong, my x-axis is completely wrong, so now I have to rescale all that so that they line up. So if I do this, right, so now I have to stretch, oh, yeah, this is going to be tricky here. I have to stretch this so it's like basically the same as, you know, 0 to 0.9, so I'm a little heavy here, heavy-handed, so here, here-ish. Okay, that looks about right. And then on the x-axis, I only have 2 orders here, but I have a bunch of orders there, so if I squeeze that in to get my 2 orders, okay, just about right there, I guess. Okay, and now that I have my axis lined up, now I can go and figure out which one of these curves do my data fit on. And this looks like it might be at 0.9 there. It's a little bit hard to go through, but yeah, I can't really do it with my mouse. But you do this manually, you move it around, and then you find that you can find a match. So here you can see the data is actually on the mu is, or log mu, I guess, is -3. So now there's 2 things you want to do. Identify mu. So again, this is, you can see that second data point is kind of off the curve, but everything else lines up nice on that -3 curve, right? So log mu is -3. Again, these curves are like log mu, right? You can see here it's written log 10 mu equals, you know, blah, blah, blah. So if log 10 mu is -3, then, you know, mu is e -3. And finally, we want to draw that line that corresponds to the y-axis, the x-axis, excuse me, equals 1. Okay, so at the x equals 1 number, sorry, I grab things when I don't mean to. Okay, I want to draw in here. Okay, so at x equals 1 here, right, I draw a line vertical, and then I'll be able to read time on my plot. So again, first line up the data, right, find the proper curve, then once you have that, read mu, then once you have that, you know, put a line basically through your data that corresponds to the x is 1 or the eta is 1 on the type curve, on the example curves, and then finally you got everything, right? So read the time, right? Read the time. So here you get t is about 15 seconds for this example. So we have mu is 1 e -3, like I said, right, from before. T equals 13 seconds. I guess that's the more precise. When you do it carefully, you get 13 seconds. Now the well casing was 7.6 centimeters in this case, and the screen casing was 5.1. You can see here the screen is actually smaller than the casing, which is not often the case, but you know, that's a configuration. So in this example, that's what's given. The aquifer itself is 5 meters deep, right? So now we got everything, right? 5 solved, right? So we got eta equals tt over rc squares equals 1, right? At t equals 13 seconds. So now we know the casing radius, we know the time, 13 seconds. We know eta is 1, right? So we can write 1 equals transmissivity times 13 divided by 7.6 squared, meaning the only unknown is transmissivity, so transmissivity equals blah, right? Mu equals 1 e minus 3 equals screen radius that we know, storativity that is the unknown, and casing radius that we know. So storativity is the only unknown, we can calculate it. So now we have a method to calculate transmissivity and storativity here from our head versus time data. And this is the first method. Now the next method is the Vorslev method, and this is typically valid when the length of the casing divided by the radius is more than 8. So basically deep wells in the confined aquifers typically. Now this is a very efficient method, it's very easy, but you don't get storativity out of it. So that's the drawdown. Let me try and get my red. Okay, so you can see here the equation, and again notice that this is very similar to all the equations we had before, right? There's R square here, the log of a ratio of length scale. So here it's like the length of the screen over the radius. And then at the bottom we have a 1 over time, which is also what we had before for the falling head, piezometer, for everything we've seen, right? Now this time here is the key for the Vorslev method. So T37, right? This is the time at which the water level is 37% of the origin. There is some stories behind picking that time, and that's mainly because this way, at this time you get a log that gives you a -1. So if you do a log of 0.37, right, that gives you -1, so it's just an easy number to move around. So that's why we picked that. But anyways, in practice, what you do is you go to 37% here on your, again, this is ratio of head, right, from 1 and then down, 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 and versus time, right? And you can see here at 37, you can go pick, oops, at the ratio 37%, you can see, you can read the time on the x-axis. So now you have the time, T37 is 4 seconds here, right? So since everything else is known, right, it's just well's characteristics, the length of the screen, the radius of the well, you read this from the graph or from the data, so you don't have any type curve, anything, you just read it straight from the graph, and then you can just plug it in and calculate your hydraulic conductivity, right? So if you know the depth of your aquifer, you get transmissivity. Now again, you don't get storativity with the Vorslev method, right? But it's very straightforward, very efficient. So here's an example where you can plug in some numbers, right, and find the hydraulic conductivity for this particular well. Another example that's in the book, I'm not going to treat it here, but you can see here that this is the example in Feather. I'm trying to find it. Sorry, I'm still struggling with this new pointer that I have here. But you can see here that T37, right, 37%, you know, regress it, and then find the time corresponding, and then if you know something about your well, so if you know the well casing and screen radius and the screen length, you can find the hydraulic conductivity for that well. Okay, another set of data, and you can see this is more real data, right, or you know, less ideal data, I guess. And you can see again the departure from the linear trend at late times, and that's pretty typical. We've already seen some of those, you know, during those lectures. So early on, you have, again, very early on, what happens is you have water that is released, you know, fast from elastic storage. So let's say this was in an unconfined aquifer, right? So very early on, you have some elastic storage, so that you have some readily available water, either elastic storage, or again, if you have a gravel, you know, gravel pack around your well, there's some high hydraulic conductivity water that's just rushing into the well, right? Or rushing out of the well, I guess, in this case. So you don't want to take that as your typical number. You want to get that second sort of straight line here, which is the one that I highlighted with the black fit, right? And you can see that this is more representative of your well. And then at late times, again, you have departure from that, so that you don't want to use that data either. You know, that's just, again, like we've seen before. Again, you can use the Vorslev method here and, you know, find the 37% point, regress that and find the time for that. But you could also use other methods that would work. For example, this is the last method we'll see for this lecture, right? The Boer and Rice method. Now, the Boer and Rice is typically for unconfined aquifer. So again, the previous two are for confined aquifer. I already explained that. This one, you know, the upside of the Boer and Rice is that it does work for an unconfined situation, which is really neat. But it also comes with a bit of added complexity. There's a lot of additional, you know, strange parameters that we'll have to deal with. I mean, it's not that hard in practice, but it's kind of weird, you know, to consider. This paper is actually in your paper folder online, so you can go and grab it. All the derivations are in there. All the plots that I have coming in the next couple slides are from that paper. It's very well written and very readable. So if, you know, I encourage you to go back to the paper if you want. Here is all the definitions again of what I've been talking about. Here they use D as the depth of the aquifer. We've been using B in this class a lot. You know, just different, different nomenclature, I guess, different convention here. D is, again, the stable water table. So this is an actual water table, right, unconfined. So the water table, the stable water table level is D. L is the length of the screen, and you can see that those wells don't actually have to be fully penetrating. So this is a, you know, we've relaxed the assumption that the wells are fully penetrating here. The casing radius are, you know, obviously the ones from the pipe up top. The well radius is, you know, the effective, you know, well size. You know, again, if you have some gravel pack here or the screen size, you can take the screen size, but this is really the well size. And H is the distance from the stable water level to the bottom of your well, which may or may not be the same as D, right? So if the well is fully penetrating, then H equals D. If it's not, they can be different, and that's why it introduces more complexities, because now we have like different terms. Now again, this is the equation, the general equation, and this is similar to what we've seen before. Again, that's 1/time log of the ratio of heads, right? This is the exact same as before. And then the slope of that line would be, you know, all those length scale, basic, or ratios of length, right, that we have to deal. Now, again, the effective radial distance here is basically the what we've called the radius of influence before. So, and this is tricky. Like, the question becomes, okay, how do I know, you know, how far that slug test is influencing, or how far I'm measuring, basically, the parameters? I've said, you know, all those methods, the slug test methods, the problem is they're usually local, like they measure not very far from the well, but, you know, not very far is how much, right? How far is that? And that's the RE problem. The effective radius is not obvious how you calculate it. So here is the skinny, right? So these are the ugly equations, but again, don't get too afraid. The point here is that the problem with the effective radius is that it depends on the other parameters in the equation here, right? So the effective radius will depend on the hydraulic conductivity, and it will depend on, you know, how big the well is and the screen is and everything. So there's some codependency between the effective radius and those variables. Now, these are resolved here. And basically, these two equations allow you to calculate this term, this ln, you know, this natural log of the effective radius over the well radius, which is that kind of weird number that is hard to, we can't really measure that directly. But these equations, if you plug in, you can see that all those numbers, all those constants here are known, right? The length of the screen, the radius of the well, again, D is the stable water level, H is the distance between the bottom of the screen, blah, blah, blah. So all those things you know, and what you don't know here is those weird constants, right? So now you have an A and a B that we don't know about. Note that if D minus H equals 0, meaning if your well is fully penetrating, right? I've seen that before. So if, you know, if this term here is, so if H equals D, now D minus D equals 0, and now we have a problem because we got log of 0, which doesn't solve, so we have to use some little different, right? So you can see this term now, A plus B, blah, 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 for a fully penetrating well is replaced by C, which is another thing. Now, how do we find those ABCs? Well, we find them from this graph here. And again, this has been tabulated, basically resolved from data from many wells and all that. And the beauty is that this is relating A, B, and C. Well, A and C on the left, B is on the right here, to the ratio of the length of the screen to the radius of the well, right? So the bigger the length of the screen, we're on that right-hand side. The bigger the radius of the well, we're on that left-hand side. But again, this is a geometric ratio that we know, right? This is something that is known from your well. So what you do is you take this ratio, you plot it, or you plug it in here, you come here, let's say we're here, and then you just literally go and read your numbers, right? So if you have an L over RW that is whatever that was that I did, like 300 or something, right? This is the number, then you can read A and B if you need to use that first equation 8 over there from the paper. Or if it's a fully penetrating well, then you don't need A and B, you just need C, so you go read C, right? And you add that to your sauce, right? You add that to the recipe, you just plug everything in, and you finally get this weird number that you can then plug back into your equation. And now you have everything you need to calculate your hydraulic conductivity. Okay, so it's a bit cumbersome, there's a couple steps here, but it's definitely doable as long as you have all the well information. Use the plots provided by the original paper of Boer and Rice, and you're good to go. So here's an example again, that's what they have in the paper. You can go back to the paper to see it. But this is the data, and this is also in Feather actually somewhere, but not as detailed. So here is the actual solved example from the paper. Again, a well, a slug test. So dropping head, you can see that we only have data, it drops real fast early on. Anyway, so we drop, and then we again get away from that linear trend, but the linear trend here is that dashed line, right? So we can see that all the parameters for the well are given here, and again, this is some well test or some slug tests that were done in actual wells, so we have the information here published in the 70s. Then you extend the straight line, you find the slope basically, and then again the value of L over RW is 38. So now you go back to your L over RW, right, is 38, so we're somewhere down here, right? So from here we go read the value of those weird constants here, right, which are given here, A and B. Then you can substitute that into equation 8, like I said before. So equation 8 here, just plug everything in, find the value of that natural log, blah, blah, blah. And then finally, you can use your general equation, so equation 5 in the paper, or this equation here from Feather, to plug everything in and find K. Okay? So this is the whole process. Here is a worked out example, basically, of the Boer and Rice method. Okay, well, that concludes our lecture for the day. I know it's quite a bit of information to go through, but yeah, so we've seen the 3 methods, the Cooper, the Vorslev, and the Boer and Rice. The first 2 were for a confined aquifer. The first one, the Cooper, is the graphical method. The second one is basically like a straight line method, right? If you remember from a couple of lectures back, where you just use your data, find that time at 37% down, and then you're good to go. And finally, the Boer method, which is a little cumbersome or a little more involved, but has the big advantage of being useful for a confined aquifer. So if you have a little piezometer like the one here on the picture, right, that you can do yourself with a 2-inch, 3-inch PVC pipe, you can drop something, and if you have a way to record the water level over time, now you can use the Boer method to find the properties around that well. So it's almost like a falling head permeameter. Okay, thank you very much, and I will see you on